This is the EdExcel Advanced Extension Award from the June 2022 series. Question number 1. We are given that f of x is equal to x to the power of x squared, where x is greater than 0. We have to use logarithms to find the x-coordinate of the stationary point of the curve with equation y equals f of x. So we begin with y equals x to the power of x squared. And now if we use logarithms, taking the natural log of both sides, we would have the natural log of y equals the natural log of x to the x squared. So on the left hand side we've got the natural log of y, but on the right hand side we can use the power law of logs, leaving us with x squared multiplied by the natural log of x. And now if we differentiate implicitly, well, differentiating the natural log of y, we would end up with 1 over y multiplied by dy over dx. And on the right hand side, using the product rule to differentiate, well, differentiating x squared, we end up with 2x, and we multiply this by the natural log of x, and then we have x squared multiplied by the derivative of the natural log of x, which is 1 over x. So we have 1 over y multiplied by dy over dx, and this is equal to 2x times the natural log of x plus x. X squared multiplied by 1 over x is just x. And if we multiply through by y, we would have dy over dx, which is equal to y multiplied by 2x times the natural log of x plus x. And knowing that y is equal to x to the x squared, we can therefore conclude that dy over dx is equal to x to the x squared multiplied by 2x times the natural log of x plus x. And now we wish to find the x-coordinate of the stationary point. In other words, if we have dy over dx equaling 0, then we have x to the x squared multiplied by 2x times the natural log of x plus x equaling 0. Now, either we have x to the x squared equaling 0, or 2x times the natural log of x plus x equaling 0. Now what we will do beforehand is we will factorize out the x. So we have x to the x squared multiplied by x multiplied by 2 times the natural log of x plus 1 equaling 0. Now from here we can see then that x to the x squared will equal 0, x will equal 0, or 2 times by the natural log of x plus 1 will equal 0. But because we know x is greater than 0, x cannot equal 0, and x to the x squared cannot equal 0. So we've got 2 times the natural log of x plus 1 equaling 0, and that's because x must be greater than 0. So if we've got 2 times the natural log of x plus 1 equaling 0, that would imply the natural log of x is equal to negative 1/2, and so x is equal to e to the negative 1/2. In other words, the x coordinate of the stationary point, we would have x equals 1 over the square root of e as our only solution. Question number 2. Figure 1 shows a regular hexagon OPQRST. The vectors p and q are defined by p equals OP and q equals OQ. Forces in newtons, FP equals OP, FQ equals 2 times OQ, FR equals 3 times OR, FS is 4 times OS, and FT is 5 times OT are applied to a particle. For part A we have to find in terms of P and Q the resultant force on the particle. Now, for us to find out what OR, OS and OT are, we need to find other vectors. Now, first of all, we can see from the diagram that OP is parallel to SR, and that's because we have a regular hexagon. So the vector SR, that's equal to the vector OP, which is equal to P. So this vector here is P. And similarly, OQ is parallel to the vector TR. So the vector TR is equal to the vector OQ, which is equal to Q. So this vector here is equal to Q. And then we can now find the vector PQ. So the vector PQ, that's equal to the vector OQ subtract the vector OP. So that's equal to Q minus P, which means that this vector is equal to Q minus P. And now, because PQ and TS are parallel, we can therefore say that the vector TS is equal to the vector PQ, which is equal to Q minus P, which means this vector here is equal to Q minus P. Now we somehow need to find the vector OR. And for me to find the vector OR, well, if I somehow know what QR is, that will help me find the vector OR. And the way we can think about this is to extend PQ and SR, like we see here, to a point U, say. And then we can see from here that the vector given by RU will also equal P. So in other words, RU is equal to OP, which is equal to P, and QU is equal to the vector PQ which is given by Q minus P. So if we add this to the diagram, we have the vector QU equaling Q minus P. So we know we have extended the lines PQ and SR to a common point U. So if we find out what QR is, the vector QR is equal to the vector QU plus the vector UR. So we have the vector QU, which is equal to Q minus P, and the vector UR, that's the negative of P, and therefore the vector QR is equal to Q subtract 2P. So if we add this to the diagram, then this vector here will equal Q minus 2P, and we can now find out what the vector OT is. So the vector OT, that's equal to the vector QR, which is equal to Q minus 2P. So this vector here is equal to Q minus 2P. Now, with all this information, we can find out other vectors. We've got OP, we've got OQ, so now let's find out what the vector OR is. So the vector OR, we can find out what that is by going from O to Q and then Q to R. So we can go from O to Q, and then we can go from Q to R. So the vector O to Q, that's Q, and the vector O to R, that's Q minus 2P, and therefore it turns out we would have 2Q subtract 2P. And now we can find out what the vector OS is by going from O to R and then R to S. So the vector OS, that's equal to the vector O to R and then R to S. So we've got the vector O to R, which is 2Q minus 2P, and then we've got the vector RS, and if we go back to the diagram we can see that RS is negative P. And now if we simplify all this, we can see the vector OS is equal to 2Q subtract 3P. And now we can find out the resultant force. So for the resultant force R, that's equal to FP plus FQ plus FR plus FS plus FT. So these are all vectors, as we see here. So we've got the vector FP equaling OP. Then we've got FQ, which is equal to twice OQ. Then we've got FR, which is 3 times by OR. Then we've got FS, which is 4 times by OS. And then we've got FT, which is 5 times the vector OT. So we've got the vector OP, which is P, the vector OQ, we found that out earlier to be equal to Q, so we add on 2Q. Then the vector OR, we found this to be 2P minus 2Q, so we've got 3 multiplied by 2 times by Q, subtract 2 times by P. Then we've got 4OS. Now OS is 2Q subtract 3P. And then we've got 5OT, and OT is given by Q subtract 2P. So if we expand where necessary, we've got P plus 2Q plus 6Q subtract 6P plus 8Q subtract 12P plus 5q subtract 10p. And simplifying all this, we end up with minus 27p plus 21q. So this is what the resultant vector r is. For part B of the question, the magnitude of the acceleration of the particle due to these forces is 13 meters per second squared. And given that the mass of the particle is 3 kilograms, we have to find the magnitude of p. So we've been given a mass, we've been given an acceleration, and we've calculated a resultant force. So that would suggest to us at some point we need to use Newton's second law to sum of the forces. The resultant force is equal to the mass multiplied by the acceleration. Now, for part B, what we need to do to begin with is find the magnitude of r in terms of p only. We want to find out what p is. So, we can rewrite r as 21 multiplied by q minus p subtract another 6p. That's the same as minus 27p plus 21q. So, if we draw a diagram, we've got r, which is equal to 21 multiplied by q minus p subtract 6p. And if we find the magnitudes, noting we have a equilateral triangle, what we would have is this triangle here. We've got a side length of r, a side length of 21 multiplied by the vector q minus p, and here a length of 6p. Now, as OPQRST is a regular hexagon, from that we can see, going back to our diagram, that the magnitude of p is equal to the magnitude of q minus p. So, the magnitude of p is equal to the magnitude of q minus p, which is just equal to p. And if we adapt our diagram, we end up with this diagram here. Now, just to explain again why we have 60 degrees here, what we have is q minus p, and then we have essentially an angle going this, a line going this way, and if this is 60, because it's an exterior angle, that means this is also 60. So, if we find the magnitude of r, we can do that using the cosine rule. So, we've got the magnitude of r, which is equal to, well, I've got 6p all squared plus 21p all squared subtract 2 multiplied by 6p multiplied by 21p multiplied by the cosine of 60 degrees. So, working this out, we've got 36p squared plus 441p squared subtract 252p squared multiplied by 1/2. Cos of 60 is 1/2. And therefore what we will end up with is 351p squared. So that's what the magnitude of r squared is. So the magnitude of the vector r is equal to 351 p squared square rooted, which is equal to 3p multiplied by root 39. And so, if we use the fact that the sum of the forces is equal to the mass times the acceleration, we've got the sum of the forces, which is 3p multiplied by root 39. That's equal to 3 multiplied by 13. So, we can see then P is equal to root 39 over 3. Question number 3. For part A, we have to use the formulae for sine of a plus minus b and cos of a plus minus b to prove that tan of 90 degrees minus theta is equivalent to cot theta. So, for part A of the question, if we focus on the left hand side, then you can see we start off with tan of 90 degrees minus theta. And recognizing that tan is equivalent to sine over cos, then tan of 90 degrees minus theta will be equivalent to sine of 90 degrees minus theta divided by the cosine of 90 degrees minus theta. And now we can use these formulae here. So, sine of 90 degrees minus theta, that is the same as the sine of 90 degrees multiplied by cos theta subtract cos of 90 degrees multiplied by sine theta, and then we will divide this by, well, here we've got cos of 90 degrees minus theta, which, using the formula, we have cos of 90 degrees times by cos theta plus sine of 90 degrees sine theta. So, sine of 90, that's 1, so we've got 1 times by cos theta, which is cos theta, and cos of 90 is 0, so we've got 0 times by sine theta, which is 0. And then cos of 90 is 0, so we've got 0 times by cos theta, which is 0. And then we add on sine 90 times sine theta, and sine 90 is 1. So we've got 1 times by sine theta, which is sine theta. In other words, we have cos theta divided by sine theta, which is equivalent to cot theta, and that's exactly what we wanted to show. So the result here is what we have on the right hand side, hence the identity is shown to be true. For part B of the question, we have to solve for theta being in between 0 and 360, the equation 2 subtract sec squared of theta plus 11 degrees equals 2 times the tangent of theta plus 11 degrees multiplied by the tangent of theta minus 34 degrees. And we have to give each answer as an integer in degrees. So, for part B of the question, we have our given equation here, and now we can use the identity for sec squared, which is 1 plus tan squared. So, we have 2 subtract, then in brackets, 1 plus tan squared of theta plus 11 which is equal to 2 times by tan of theta plus 11 multiplied by the tangent of theta minus 34. And now we can see here we've got 2 subtract 1, which is 1, and then we've got minus tan squared of theta plus 11 equals 2 tan of theta plus 11 multiplied by the tangent of theta minus 34. And now what we can do is divide through by tan of theta minus 34 and 1 minus tan squared of theta plus 11. And if we do that, then we would have 1 divided by tan of theta minus 34 equaling, now here we would have 2 times by the tangent of theta plus 11 divided by 1 minus tan squared of theta plus 11. And now what we can do is recognize on the right hand side something of the form tan 2a being equivalent to 2 tan a over 1 minus tan squared a, where a is theta plus 11. And so the left hand side would remain the same as 1 divided by tan of theta minus 34, but the right hand side is of the form tan of 2 multiplied by theta plus 11, as we see here. So if we recognize that 1 over tan of theta minus 34 is the same as cot of theta minus 34, well, that's what we have on the left hand side, and on the right hand side, expanding, we would have the tangent of 2 theta plus 22. Now, if we use what we found in part A, we know that cot theta is equivalent to the tan of 90 degrees minus theta. So the cot of theta minus 34, that is the same as the tangent of 90 minus theta minus 34, and that's equal to tan of 2 theta plus 22. So we've got tan of 124 minus theta equaling the tangent of 2 theta plus 22. So we would have 124 minus theta equaling 2 theta plus 22. And therefore 3 theta is equal to 102, and because we are finding multiple solutions, we need to add on 180k, where k is a integer. Now, our original domain was from 0 to 360. This time we've got a 3 theta, so if we write down our new domain will be this time from 0 to 3 theta to 1080. So if we solve for 3 theta, well, when k is 0, we have 102, and essentially what we're doing each time is we're adding on 180. So if I add on 180, I get 282, add on another 180, we have 462, add on another 180, we have 642, another 180, we have 822, and if I add on another 180, we have 1002. And therefore, if we divide through by 3 to find out what theta is in the correct domain, we would have 34, 94, 154, 214, 274, and 334. Question number 4. We're given that f of x is equal to e to the x cubed minus 2x, and for part A we have to find f dash of x. So, for part A, if we are given f of x equals e to the x cubed subtract 2x, then f dash of x, well, we multiply by the derivative of the power, which is 3x squared subtract 2, and then we multiply this by e to the x cubed subtract 2x. So f dash of x is equal to 3x squared minus 2 multiplied by e to the x cubed minus 2x. For part B of the question, the curves C1 and C2 are defined by the functions g and h respectively, where g of x is equal to 8x cubed multiplied by e to the x cubed minus 2x, and h of x is equal to 3x to the 5 plus 4x multiplied by e to the x cubed minus 2x, where x is a real number and x is greater than 0, and we have to find the x coordinates of the points of intersection of C1 and C2. So for part B of the question, if we set those functions equal to each other, we have 8x cubed multiplied by e to the x cubed subtract 2x, and this is equal to 3x to the 5 plus 4x multiplied by e to the x cubed subtract 2x. And now if we take everything over to one side and then factorize out the e to the x cubed minus 2x, we would have 3x to the 5 subtract 8x cubed plus 4x multiplied by e to the x cubed subtract 2x. This is equal to 0. So either we have e to the x cubed subtract 2x equaling 0, or we have 3x to the 5 subtract 8x cubed plus 4x equaling 0. Now here, e to the x cubed minus 2x cannot equal 0, so we are only left with 3x to the 5 minus 8x cubed plus 4x equaling 0. So if I factorize out an x, we have x multiplied by 3x to the 4 minus 8x squared plus 4 equals 0. And factorizing even further, we have x multiplied by 3x squared minus 2 multiplied by x squared minus 2. This is equal to 0. And therefore, if we write down the solutions for this, we have either x is equal to 0, 3x squared minus 2 equals 0, x squared minus 2 equals 0, which means x is equal to 0, x is equal to plus minus 2/3 square rooted, or x is equal to plus minus the square root of 2. Now, as x is greater than 0, we would therefore have solutions of x equals positive 2/3 square rooted, or positive square root 2 as our only solutions. For part C of the question, given that C1 lies above C2 between these points of intersection, we have to find the area of the region bounded by the curves between these 2 points, and we have to give our answer in the form a plus b e to the c, where a, b and c are exact real numbers to be found. Well, here is a sketch of what's going on. We've got h of x and we've got g of x, and between the 2 points of intersection we see that g of x is above h of x. And what we need to do is find out the area between the 2 points of intersection. The area is shown shaded. Now, we've got one of those points of intersection over here, and we've got another one which is over here. Now, we've got 2/3 square rooted, and we've got 2 which is being square rooted. Now, square root 2 will obviously be bigger than the square root of 2/3. So, this point here is square root 2. So, we've got another point of intersection which is square root of 2/3, and if we make a note, then if we have the square root of 2/3, we can rewrite this as 2/3. Well, we can rewrite this as square root 2 divided by square root 3, which is equal to square root 2 divided by square root 3 multiplied by square root 3 divided by square root 3, which is the same as, well, we've got here root 2 times root 3, which is root 6, root 3 times root 3, which is 3. So, the square root of 2/3 is the same as root 6 over 3. So now we need to find the required area. So the required area, that's equal to the integral of g of x subtract h of x dx, and we will be integrating between alpha and beta, where alpha is equal to root 6 over 3 and beta is equal to root 2. So if we integrate then between alpha and beta, well, g of x, that's equal to 8x cubed times e to the x cubed subtract 2x, and h of x is equal to 3x to the 5 plus 4x e to the x cubed subtract 2x dx. Now what we can do is factorize out an e to the x cubed minus 2x, and if we do that, we've got the integral between alpha and beta of 8x cubed subtract 3x to the 5 plus 4x multiplied by e to the x cubed subtract 2x dx. And so, if we factorize out an x from this bracket, we've got the integral between alpha and beta of x multiplied by, well, what we'll do is we'll factorize out a minus 1 from the integral. So we've got the integral between alpha and beta, and then we have 3x to the 5 subtract 8 x cubed plus 4x, and then we have e to the x cubed subtract 2x dx. So we've got minus, and then the integral between alpha and beta, and what I can do is factorize out an x. So I've got an x multiplied by 3x to the 4 subtract 8x squared plus 4, then I've got e to the x cubed subtract 2x dx. And now we can factorize this bracket even further. So I've got minus this integral, then I've got the x, and then I can rewrite all this as 3x squared minus 2 multiplied by x squared minus 2 e to the x cubed subtract 2x dx. So, simplifying this even further, well, what we'll do is we'll multiply the x into this bracket x squared minus 2, because then it will look similar to this power here. So, doing so, we've got minus the integral from alpha to beta of x cubed subtract 2x, then I have 3x squared minus 2 e to the x cubed minus 2x dx. Now to integrate this, we can use integration by parts. So if we use integration by parts, if I say that u is equal to x cubed minus 2x, And from this we can work out what u dash is. That's 3x squared minus 2. And v dash, that will equal 3x squared minus 2 e to the x cubed subtract 2x. And the reason I want v dash to equal this, well, notice what we did in part A when we found f dash of x. We found f dash of x to equal this, and if I integrate this, I end up with f of x. So that means v will simply equal e to the x cubed subtract 2x. And at this point we can find out the integral by applying by parts. So we can say that the area then is equal to minus the integral of, well, I've got all this result here, and if I use by parts, the minus is going to stay where it is, and if I open up curly brackets, what we have is u times by v, so we'll put this in a square bracket. We've got u times by v, which is x cubed subtract 2x multiplied by e to the x cubed subtract 2x. So that's what u times by v is. And I'm evaluating this between alpha and beta. And then I subtract the integral of v u dash. So we have v u dash between alpha and beta equaling, well, I've got here 3x squared minus 2 e to the x cubed subtract 2x dx. So working this out then, well, we've got the minus, and then here this result stays the same. So we've got x cubed minus 2x e to the x cubed subtract 2x being evaluated between alpha and beta, and then we subtract. Well, if I integrate this, well, similar idea to what we did over here, what we will end up with is e to the x cubed subtract 2x in between alpha and beta. And now if we expand the minus inside, what we will have is minus x cubed minus 2x e to the x cubed subtract 2x. And then I've got the minus and the minus, which give a plus. Then I have e to the x cubed minus 2x. And all of this is evaluated between alpha and beta. And now we can factorize out an e to the x cubed minus 2x. So I'm evaluating e to the x cubed minus 2x, and then what would go inside this bracket is 1 minus, and then in brackets, x cubed minus 2x. And this is going to be evaluated between alpha and beta. So simplifying even further, we have e to the x cubed minus 2x, and then here we've got 1 minus x cubed plus 2x, and then close this bracket. We're evaluating this between alpha and beta. So now we need to substitute in for alpha and beta, which we know is root 6 over 3 and root 2. So if we work out what this is, for our upper limit, we have e to the power of root 2 cubed, subtract 2 times by root 2, multiplied by 1 minus root 2 cubed plus 2 root 2. So that's what we have for our upper limit. And then for our lower limit, we replace the x with root 6 over 3. So we have e to the, well here, we have root 6 over 3 cubed, subtract 2 times by root 6 over 3, and then we multiply this by 1 minus root 6 over 3 cubed plus 2 times by root 6 over 3. So now we need to simplify all this. So here, for our upper limit, we have e to the power of, now here root 2 all cubed, that's just going to be 2 root 2, and then we subtract 2 root 2, and then we multiply this by 1 minus 2 root 2 plus 2 root 2. For our lower limit, well, root 6 over 3 all cubed, that's going to be 6 root 6 over 27. So we have e to the 6 root 6 over 27 minus, and then here we have 2 root 6 over 3, and this is being multiplied by 1 minus, well here we've got 6 root 6 over 27 plus, and then here we've got 2 root 6 over 3. So now let's attempt to simplify all this. Well, for the upper limit, we've got e to the 2 root 2 minus 2 root 2, so that's just going to equal e to the 0. And then inside the bracket, we've got 1 minus 2 root 2 plus 2 root 2, which is just 1. And then for the lower limit, we would have E. Now here we've got 6 over 27 minus 2/3, so that is the same as 6 over 27 minus 18 over 27, so that will be minus 4 root 6 over 9. So here we have e to the minus 4 root 6 over 9. And then if we open up our bracket, we have 1 minus, and then here we have 4 root 6 over 9. And so what we will end up with then is the area equaling 1 minus, then here we have 4 root 6 plus 9 over 9, so that's just combining these fractions, and then we multiply this by e to the minus 4 root 6 over 9. So this is the required area. Question number 5. An aeroplane leaves a runway and moves with a constant speed of v km per hour due north along a straight path inclined at an angle arctan of 3/4 to the horizontal. A light aircraft is moving due north in a straight horizontal line in the same vertical plane as the aeroplane at a height of 3 km above the runway. The light aircraft is travelling with a constant speed of 2 km per hour. At the moment the aeroplane leaves the runway, the light aircraft is at a horizontal distance d kilometers behind the aeroplane. Both aircraft continue to move with the same trajectories due north. For part A, we have to show that the distance d kilometers between the two aircraft t hours after the aeroplane leaves the runway satisfies d squared equals 6/5 vt minus d squared plus 3/5 vt minus 3 squared. Well, first of all, given the information about arctan, we can form a 3, 4, 5 right-angled triangle. You see that sine alpha is 3/5, cos alpha is 4/5, and tan alpha is 3/4. So let's draw a diagram to illustrate what's going on. So there's alpha. So here what we have is the runway, and then if I draw a line like this, here is where the aeroplane is. So let's write that down. Here we've got the aeroplane, and the distance it would have been at this point, if this angle is alpha, then what we have here well, we've got the speed v, and if I multiply the speed by the time I get the distance, so the distance will be vt cos alpha, and we also have vt sine alpha in the y direction. And knowing what cos alpha and sine alpha are, we can write this coordinate as 4/5 vt, then 3/5 vt. And then we've got the aircraft as well, which is over here somewhere. So let's write this down. We've got the aircraft at this point here, and the coordinates of this point, well, the distance it's travelled, we've got the speed 2v, and if I multiply that by the time, we've got 2vt, but then we subtract d because it's d behind the aeroplane horizontally. And then the y coordinate, well, what we also know is it's 3 kilometers above the runway, so the y coordinate is 3. So this is essentially what's going on, and we need to find out the distance between them. So what we have is d squared equaling the change in the x's essentially. So that will equal 4/5 vt, then we subtract, and here we've got 2vt minus d. Then we square this, and then for the y coordinates, well, we have 3/5 vt subtract 3, then squared. So now let's try to simplify all this. Well, here we've got 4/5 vt minus 2 vt plus d. Then this is squared, and then here we have 3/5 vt subtract 3 squared, and therefore simplifying this even further, we've got 4/5 vt minus 2 vt. That will be minus 6/5 vt, and then we add on d, then this is squared, and then we add on 3/5 vt minus 3 squared. And if I take out a minus 1 from this bracket and then square it, we've got minus 1 squared, and then here we would have 6/5 vt minus d squared plus 3/5 vt minus 3 squared. A minus 1 all squared is just 1. So what we will be left with is 6/5 vt minus d squared plus 3/5 VT minus 3 squared. And that's exactly what we wanted to show. Now for part B, given that the distance between the two aircraft is never less than 2 kilometers, we have to find the range of possible values for D. Now, what we can say from here then, for part B, is D, the distance between them, is never less than 2. So D must be greater or equal to 2, which would imply that D squared is greater or equal to 4. And therefore, what we would have is 6 VT over 5 minus D squared plus 3 VT over 5 subtract 3 squared is greater or equal than 4. So now let's try to expand and simplify. Well, if I expand this bracket, what we will have is 36 V squared T squared over 25 minus 12 VTD over 5 plus D squared plus, now here we would have 9 V squared T squared over 25 minus 18 VT over 5 plus 9 being greater or equal than 4. And if we gather all like terms together, well, 36 over 25 plus 9 over 25, that will be 45 over 25, which we can simplify to 9 over 5. So we've got 9 over 5 VT all squared minus, and then in brackets we would have 12D plus 18 over 5 VT plus D squared. Now here we've got 9 subtract 4, which is 5. So we've got plus D squared plus 5. This is greater or equal than 0. So as we've got a quadratic which is positive, it cannot have any solutions when you set it equal to 0, which means the discriminant is less than 0. So we've got b squared minus 4ac being less than 0, which means we've got b squared, so that is minus 12d plus 18 over 5 squared minus 4 times by a, which is 9/5, times by c, which is d squared plus 5, this is less than 0. So if we try to simplify, well, minus 1 all squared is just going to be 1. And if I factorize out a 6 from the 12d plus 18, well, what we would have then is 6 multiplied by 2d plus 3 all over 5 squared minus 36 over 5 multiplied by d squared plus 5. This is less than 0. So we've got 36 over 25 multiplied by 2d plus 3 squared minus 36 over 5 multiplied by d squared plus 5 being less than 0. And if I multiply through by 25 and then divide through by 36, we would have 2d plus 3 squared minus 5 multiplied by d squared plus 5 is less than 0. So we've got 4d squared plus 12d plus 9 minus 5d squared minus 25 is less than 0. So we've got minus d squared plus 12d minus 16 is less than 0. So d squared minus 12d plus 16 is greater than 0. And if we attempt to complete the square, we've got d minus 6 all squared minus 36 plus 16 is greater than 0. D minus 6 all squared is greater than 20. And if we find our critical values, we've got d equals 6 plus minus 2 root 5. And if I draw a quick sketch to help solve this, such as the one here, we've got 6 minus 2 root 5, and then we've got 6 plus 2 root 5. We are looking for where this is positive, which is here and here, and therefore for the solutions we would have d, which is greater than 6 plus 2 root 5, and we also have d, which is less than 6 minus 2 root 5. Question number 6. Figure 2 shows the first few iterations in the construction of a curve L. Starting with a straight line L0 of length 4, the middle half of this line is replaced by 3 sides of a trapezium above L0, as shown, such that the length of each of these sides is 1/4 of the length of L0. And that's what we see here. After the first iteration, each line segment has length 1. In subsequent iterations, each line segment parallel to L0 similarly has its middle half replaced by 3 sides of a trapezium above that line segment, with each side 1/4 of the line, with each side 1/4 of the length of that line segment. Line segments in Ln are either parallel to L0 or sloped. For part A, we have to show that the length of L2 is 23 over 4. So what essentially this question is saying is, we've got this straight line, and the middle half is replaced by a trapezium, as we see here. And then every part which is parallel to L0, so this is parallel to L0, so's this, those parallel lines are replaced by trapeziums, as we see here. So those original lines are replaced by trapeziums as we see here. And then these lines, which are still parallel to L0, we build into those trapeziums as we see here. So that's what is happening. Now what we need to do is show that the length of L2 is 23/4. So here for part A, we've got our diagram, and what we know already is L0 is equal to 4. We've got a length of 4. The length of L1, we can work that out. Well, what we have are 5 pieces, 1, 2, 3, 4, 5. And each of those pieces would have a length 1/4 of the length L0, which is 4. And by the way, we were told that each length of these is equal to 1. 1/4 of 4 is equal to 1. So the length of L1 then is equal to 5. And then for L2, well, to work out the length of L2, what we have is this length here and also this length here. So this length and this length have a length of 1/4 times by 4. But then we've got 2 of them. So we've got 2 times by 1/4 times by 4. And then what we have is these other pieces. Now, each of these pieces will have length 1/4 of this length, and this length, and those lengths are 1/4 of 4. But then each of those parts has 1, 2, 3, 4, 5 parts to them. And we've got that repeated 3 times. And so the length of L2, well, we've got 1 times by 2, which is 2. Here we've got 5 times by 3, which is 15, divided by 4, that's 15/4. 15/4 plus 2, you will find that to equal a length of 23/4. For the next part, we have to write down the number of line segments in Ln that are parallel to L0. Well, L1, that's got 3 horizontal line segments parallel to L0. We've got 1, 2, 3. L2, that's got 9 horizontal line segments parallel to L0. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. L3 has 27 horizontal line segments parallel to L0. So we've got 3, 6, 9, 12, 15, 18, 21, 24, and 27. So can we generalize this? Well, 3 is the same as 3 to the 1. 9 is the same as 3 squared. And 27 is the same as 3 cubed. And so, Ln would have 3 to the n horizontal line segments parallel to L0. So here we've got a 1, here we've got a 1. Here we've got a 2, here we've got a 2, here we've got a 3, here we've got a 3, here we've got an n, and here we've got an n. Now we have to write down the number of slope line segments in L2 that are not in L1. Well, each horizontal line splits to 3 new horizontal lines and 2 new sloped lines. And so 3 times by 2 is 6, so we have 6 sloped line segments in L2 that are not in L1. Now we have to write down the number of new sloped line segments that are created by the n+1th iteration. Well, each horizontal line splits into 2 new sloped lines, and therefore we have 2 times 3 to the n new slope line segments that are created by the n+1th iteration. And where this 3 to the n comes from is what we worked out here in part BI. Now for part C, hence find the length of Ln as n tends towards infinity. Now to find the general form, what we need to do is consider the total length for Ln by considering the horizontals and the slopes. So if we consider the length of the slopes, we've got S0. Well, going back to the diagram, we've got no slopes here. So S0 has slope length 0. If we think about S1, well, we've got our previous iteration 0, and then we add on to this the 1, 2 slopes we've got. So we add on 2 times by the slopes there, which is 1. Remember, each of those segments has length of 1. So this 1 comes from the fact that in this question we are told that after the first iteration each line segment has length 1. And now if we consider S2, well, going back to S2, we've got the 0 from here, and then we've got this bit and this bit which remain the same. So we've got 0 plus 2 times by the 1. But then we've got more slopes. We've got the slopes here as well to think about. And we've got 3 because we've got 1, 2, 3 of them, times by 2 because each has 2. So we have 3 times by 2, and then the length of each of these bits, well, that will be 1/4 of this bit over here. And because this is 1, what we have is 3 times by 2 times 1/4 of 1. So that is the length of the slope for S2. Now let's think about the slope S3. Well, if we think about S3, we've got this bit which remained the same from before. So we have the 0 plus the 2 times by the 1. And what else remains the same will be this slope here. So we've got 1, 2, 3, 4, 5, 6 of them. Now, ultimately in this question, we want to generalize. Now, the way we can generalize is, well, what we'll do is we'll take a look at S3. We can write this as 0 plus 2 times by 1 plus, now here I've got 3 times by 2 times by 1/4, but then here I've got 3 times by the 3, so that's 3 squared, and then I've got 1/4 times a quarter, so that's 1/4 squared, but then I'm multiplying it by 2. So can we spot any pattern? Well, here I've got 3 to the 1 times by 1/4 to the 1. So if we rewrite this, we can say we've got 0 plus, well, we could rewrite this as 3/4 to the 0 times by 2. And then here, we've got 3 to the 1 times 1/4 to the 1. So we can rewrite that as 3/4 to the 1 times 2. And then here we've got 3 squared times 1/4 squared times 2. So we can rewrite that as 3/4 squared times 2. Did we spot any pattern? What would you predict if we had S4? Well, S4, we would have something looking like 0 plus 3/4 to the 0 times 2 plus 3/4 to the 1 times 2 plus 3/4 squared times 2, and then we would add on 3/4 cubed times 2. So perhaps with the others we can generalize those even further. So for example, if we move all this down slightly, S1, could we rewrite that as 3/4 to the 0 times 2, and then could we rewrite the S2 as well? Well, if we were to rewrite the S2, well, we could potentially rewrite that as 3/4 to the 0 times 2 plus 3/4 to the 1 times 2. So a pattern is emerging. And then what we also have is the 0 as well with it. Now I'm just going to remove the 0 here. So that is the length of the slopes for S4. So if we were to generalize for, well, what would we generalize for? If we were to generalize for Sn, well, the problem with working out Sn is we've got this S0 and we can't really generalize for S0. But what we can do is think about what we would have for Sn plus 1. Because if you notice, for the 4 for example, that's 1 more than the 3 here. And the 3 is 1 more than the 2 here. And the 2 here is 1 more than the 1. And the 1 is 1 more than the 0. So that's why we consider Sn plus 1 instead. So for Sn plus 1, we would have 3 over 4 to the 0 times 2. And then we have 3/4 to the 1 times 2. And then we've got 3/4 squared times 2. And then we've got 3/4 cubed times 2. And then in general, our final term will be 3/4 to the n times by 2. And then it matches up with everything else we have. And we can write this as a summation. And if we were to rewrite this as a summation, well, from each term we can factorize out a 2. And then we've got the sum of 3/4 to the r. But then we start off at r equals 0. And we finish at r equals n. Because when r is equal to 0, we would have S1 and so on and so forth. So that is the general form for Sn. So considering the length of the horizontals, now if we go back to our diagram, H0, that's got a length of 4. So we know H0 is equal to 4. Now if we find out the length of the horizontals from H1, well, we've got 1, 2, 3 of them. So for H1 I would have 3 times by, and the length of each of those horizontal bits is going to equal 1/4 of 4. And if we think about the horizontals for H2, well, how many horizontals would I have for H2? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I think about what we mentioned before, Ln has 3 to the n horizontal line segments parallel to L0. So for L2 we would have 3 squared horizontal line segments. And the length of those will be, well, I'm going to have 1/4 of the previous length, which is 1/4 times 4. So what we're saying over here is each of these is going to be 1/4 of that. And if we can rewrite this in some way, well, we can rewrite this as 3 squared times by a quarter squared times by 4. Or perhaps more generally, 3 over 4 squared times by 4. What about h3? Well, h3, we would have 3 cubed horizontal line segments. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 21, 24, 27, or in other words, 3 cubed. And the length of each of those will be a quarter of what we have previously. So these 3 will be a quarter of that, and we've already worked out what this is. This length is a quarter of that. So here we have 3 cubed times by a quarter of, essentially, a quarter times 4. So what would we have here then? Well, for h3, we would have 3 cubed times by a quarter cubed times by 4. And more generally, we would have 3 quarters cubed times by 4. So what would you predict we will have for h4? Well, for h4 then, we predict we will have 3 quarters to the 4 times by 4. And can we generalize this? Well, let's generalize for hn plus 1. Now, why hn plus 1? Well, for the slopes, we considered Sn plus 1, so it would make sense for us to have hn plus 1. And you'll notice the 4 here matches with the 4 here, the 3 here matches with the 3 here, so on and so forth. So for hn plus 1, because we don't want to consider the h0 with it, we will have 3 quarters to the n plus 1 times by 4. And so, let's see if we can rewrite this. Well, what this is the same as is 3 to the n plus 1 divided by 4 to the n plus 1 times by 4. So, rewriting using commutativity laws, we have 3 to the n plus 1 times by 4 over 4 to the n plus 1. And therefore what we'll end up with is 3 to the n plus 1. Now 4 divided by 4 to the n plus 1, that's just going to be a quarter to the n. So we can rewrite this as a quarter to the n. So we have 3 to the 1 times 3 to the n, which is the same as 3 to the n plus 1, times by a quarter to the n. So what we end up with then altogether is 3 multiplied by 3 quarters to the n. So that's the length of the horizontals. So what we need to do now is find out a formula for the total length. So therefore, for the total length Ln plus 1, we have twice the sum from r equals 0 to r equals n of 3/4 to the r plus 3 multiplied by 3/4 to the n. And what we need to do is see what happens when n tends towards infinity. Well, as n tends towards infinity, well, here we've got a geometric series. 2 multiplied by the sum from r equals 0 to r equals n of 3/4 to the r. Well, we've got twice of, well, because we've got a geometric series, the first term is going to be 3/4 to the 0, which is 1. And then we're going to divide this by 1 subtract the common ratio, which is 3/4. And if we work this out, we get 8. So we've got a geometric series to infinity, which is why we've got this result here. And then 3 multiplied by 3/4 to the n. As n tends towards infinity, 3/4 to the n will tend towards 0, so this term will tend towards 0. And therefore, as n tends towards infinity, L infinity will tend towards 8 plus 0, which is just 8. Now for the next part, the area enclosed between L0 and Ln is An. We have to find the value of A1. So we want to find out the area of this trapezium over here. Now here we've got that trapezium. We've got lengths 1, 1 and 1 here. And if this total length is 4, then 4 subtract this one and this one is 2. And you can imagine us having some sort of symmetry about this line, which makes this a hexagon. And that means that each of these angles over here will be 60 degrees. So we have this angle being 60 degrees, from which we can find this perpendicular height. If I've got one here and one here, this height would be 1 times by sine 60, which is just sine 60. So if I find out the area of this trapezium, A1, we would have the sum of the parallel sides, 2 plus 1, multiplied by the height, which is sine 60, and then we divide that by 2. So the area of A1 is equal to 3√3 over, or sine 60 is √3 over 2, and I'm multiplying that by 3 over 2 to get 3√3 over 4. For part E of the question, we have to find in terms of n an expression for a n plus 1 subtract an. Well, an plus 1 subtract an, we're looking at the increase in the areas. So we know that the length scale factor is 1/4, and so the area scale factor is 1/4 squared, which is 1/16. So from the first to the second, we have 3 new trapezia, 1/16 the area of the first one in the first iteration. And in the n plus 1th iteration, the new trapezia have area 1/16 to the n, and there are 3 to the n such, and so we can say that the area increases by 3 to the n times by 3√3/4 times by 1/16 to the n. Now for part f, hence find the value of an as n tends towards infinity. So for part f, we have a infinities, which is what we're finding. That's equal to a1 plus a2 plus a3 plus a4, and essentially we're going up to infinity, so we could continue on. Now a1, we already know what that area is. That's equal to 3√3/4. And then a2, well, the area will increase by 3 to the n times by 3√3/4 times 1/16 to the n. So here we times this area by 3 to the 1 times by 1/16 to the 1. So if I times that area, like so, and then divide by 4, this is a2. And then a3, we're going to times this result by another 3 to the 1 times 1/16 to the 1. So in other words, it's the same as multiplying this by 3 squared times by 1/16 squared, and then I multiply this by 3√3/4. And then for the next one, we've got 3 cubed times by 1/16 cubed and then I'm going to times by 3√3/4. And then we could continue. So we've got 3√3/4 plus 3/16 to the 1 times by 3√3/4. And then for the next one, we have 3/16 squared times by 3√3/4. And then for the next one, we have 3/16 cubed times by 3√3/4, and then we could continue. And what you'll find here is we've got a geometric series. Our first term is 3√3/4, and then we're going to divide this by 1 minus the common ratio, so this is a sum to infinity, and the common ratio is 3/16. So we have over here 3√3/4 over 4 multiplied by 1 over 13 over 16, which is 16 over 13, and it turns out the area to infinity then is 12 root 3 over 13. Now for part G, the same construction as described above is applied externally to the three sides of an equilateral triangle of side length A. Given that the limit of the area of the resulting shape is 26 root 3, we have to find the value of A. Now to do this question, let's draw a series of diagrams. We start off with this triangle, and each of these sides we apply this construction. So for the next one, we replace this one with the trapezium situation for each of the sides. So here is A1 and here is A2, and then we continue on up to A3, A4, so on and so forth. Now each of these sides of a triangle have length A. So let's first of all find out the area of this triangle. So the area of a triangle, we've got 1/2 times by A squared times by sine 60. It turns out the area of the triangle is A squared root 3 over 4. Now why is that important? Now before we do anything else, what we need to notice is the area scale factor will be A over 4 squared. So now we can find the limiting area of the shape. So for the limiting area of the shape, well, we've got the area of the triangle, which we know is A squared times the square root of 3 over 4. And then we need to add on the limit of continuously adding on these trapeziums. Now if we continuously add on those trapeziums, well, we know that as A tends towards infinity for the trapeziums, the area of all those will limit towards 12 root 3 over 13. So we have 12 root 3 over 13, which we need to add on. But the thing is, that's for one of those lengths. So if we go back to the diagram, that's when we have one length and continuously add on. But we've got 3 of those lengths because we've got 3 sides of a triangle. So we need to multiply this by 3, but then we also need to multiply by the area scale factor A over 4 squared. And the reason we need to multiply by the area scale factor is because instead of us having a length of 4, we've got this time a length of A. And we know that the limit of all this is equal to 26 root 3, as we see here. Now the root 3's cancel everywhere, so what we are left with is a squared over 4 plus 3a squared over 16 multiplied by 12 over 13. This is equal to 26. So, with that, if I factorize out an a squared, we have 1/4 plus, now here we've got 3 over 16 being multiplied by 12 over 13, and this is equal to 26. Now, the 12 divided by the 16, that would give 3/4. So I've got a squared multiplied by 1/4 plus 3 times by 3 over 4 times by 13 equaling 26. So we have a squared multiplied by 1/4 plus 9 over 52 equals 26. So now combining, we've got a squared multiplied by 13 plus 9 over 52. So what we have is 22 over 52, which is 11 over 26. So I've got 11 a squared over 26, which is equal to 26. A squared is equal to 26 squared over 11. So now if we square root, we can conclude a is equal to 26 divided by the square root of 11, because I've got the square root of the square of 26, which is just 26. So this is what a is equal to. Question number 7. A circle C has centre x with coordinates a, b and radius r. Line L has equation y equals mx plus c. For part A, we have to show that the x coordinates of the points where C and L intersect satisfy m squared plus 1 x squared. Subtract 2 multiplied by a minus m multiplied by c minus b x plus a squared plus c minus b all squared minus r squared equals 0. So for part A of the question, we've got our curve x minus a squared plus y minus b squared equals r squared. We've got the centre being at AB. Let's call this equation 1. And if we take a look at L, we have y equals mx plus c. We'll call this equation 2. So what we will do is substitute in equation 2 into equation 1 to eliminate the y's. So we have x minus a squared plus mx plus c minus b squared equals r squared. And what we will do is we will write this c minus b inside a bracket, like so. It makes the arithmetic easier to work out when we expand. So if we expand out, well, we have x minus a multiplied by x minus a plus mx plus c minus b multiplied by mx plus c minus b equals r squared. So we've got x squared, subtract 2ax plus a squared plus, now here we've got mx times mx, which is m squared x squared, and then we've got twice mx times by c minus b, so that's 2mx times by c minus b, and then we've got c minus b all squared. Then if I subtract r squared and set this equal to 0, we have the result shown here. Now if I take a look at the x squareds, I've got m squared plus one of them. So I've got m squared plus 1 x squared. And if I take a look at the x's, well, if I take out a negative 2 and then open up the big bracket, I would have here a, and then I would have minus m multiplied by c minus b, close big bracket, x plus, well, I've got the a squared, and then I've got the c minus b squared minus r squared equals 0. And that's the result we wanted to show. So hence shown. For part B of the question, given that L is a tangent to C, we have to show that C equals B minus MA plus minus R multiplied by the square root of M squared plus 1. Well, here we would have to use the discriminant. And if we were to use the discriminant, first of all, we have A, which is equal to M squared plus 1, B, which is equal to minus 2 multiplied by a minus m times by c minus b, and then I've got c, which is equal to a squared plus c minus b squared minus r squared. And so if we were to use the discriminant, b squared minus 4ac equals 0, because we've got L being a tangent, we've got b squared, so that will be minus 2 multiplied by a minus m times by c minus b, and then this is squared. Then we subtract 4 times by a, which is m squared plus 1 times by c, and c is a squared plus c minus b squared minus r squared, and we set this equal to 0. So if we simplify, we would have 4 multiplied by a minus m times by c minus b squared, and then we've got minus, and then here we have, if I expand the 4 into the bracket, we have 4m squared plus 4 being multiplied by a squared plus c minus b squared minus r squared, close bracket, equals 0. So if we attempt to expand, Well, we have 4 multiplied by, well, if I expand this over here, we have a squared minus 2am multiplied by c minus b plus m squared times by c minus b squared, close big bracket, and then we have minus, well, what we'll do here is we'll expand the brackets, so we have the minus 4m squared times by a squared, so that is, well, what we'll do is we'll leave this alone as minus 4m squared plus 4 multiplied by a squared plus c minus b squared minus r squared equals 0. So if we continue, well, let's expand everything out. We've got 4 a squared minus 8am times c minus b plus 4m squared times by c minus b squared, and then I've got minus 4m squared times by a squared, so that's minus 4m squared a squared. Then I've got minus 4m squared times by c minus b all squared, so that will be minus 4m squared times by c minus b squared. Then I've got minus 4m squared times by minus r squared, so that will be positive 4m squared r squared. And then I've got minus 4 times by a squared, so that's minus 4 a squared. Then I've got minus 4 times by c minus b all squared, so that is equal to, well, we will leave this as minus 4. And then if I open up the bracket, we've got a squared plus c minus b squared. We'll move it down here. And then we've got the minus r squared. This is equal to 0. So now what we can do is divide each term by 4. And if we do that, we have a squared minus 2am times by c minus b plus m squared times by c minus b squared minus m squared times by a squared and then we have the minus m squared times by c minus b squared. We'll put the minus here. And then we have the plus m squared r squared minus a squared and then what we would also have is well, just correcting ourselves, this bit was already expanded. So now this bit can go in a bracket, so we've got minus. Then here we've got a squared plus c minus b squared minus r squared equals 0. So now what we can do is expand this bracket out. So if I do that, I would have a minus a squared, then I would have the minus c minus b all squared, and this will be a plus. So now if we see what cancels, well, the a squared and the minus a squared cancel, and then we have the m squared times c minus b all squared cancelling with the minus m squared times by c minus b all squared. Then we've got the, well, that's all we'll be left with. So if we tidy up even further, what we can say then is we've got minus 2 am times by c minus b, and then we've got the minus m squared a squared, then we've got plus m squared r squared, then we've got minus c minus b all squared plus r squared equals 0. So if I multiply through by minus 1, we have c minus b squared plus 2am times by c minus b plus m squared a squared minus m squared r squared minus r squared equals 0. Now the thing is, over here, if we take a look at what we want to show, we've got c equals b minus ma plus minus r times by the square root of m squared plus 1. So it looks like what we have to do is solve this quadratic. So if we solve this quadratic, what we will have by completing the square, you can think of this c minus b all squared being x squared. Well, let's just write this down actually. If we let lambda equal c minus b, then we have lambda squared plus 2am lambda plus m squared a squared minus m squared r squared minus r squared equals 0. So we've got lambda plus am all squared minus a squared m squared, and then we add on the rest of this and it's all equal to 0. So we've got minus a squared m squared plus m squared a squared. Well, those will simplify to 0, and therefore we will be left with lambda plus am squared equaling m squared r squared plus r squared. So knowing that lambda is c minus ab, we have c minus b plus am squared equals m squared r squared plus r squared. And at this point, if we factorize out an r squared, well, we've got c minus b plus am squared equals r squared multiplied by m squared plus 1. So we've got c minus b plus am a square root. We've got c minus b plus am equaling plus minus, because we're square rooting, r squared times by m squared plus 1. Then this is square rooted. So we've got the square root of r squared, which is just r. So we've got c minus b plus am equals plus minus r times by m squared plus 1 square rooted. And therefore, we can conclude c is equal to b minus am plus minus r times by m squared plus 1 square rooted. Next, the circle C1 has equation x squared plus y squared equal minus 16 equals 0, and the circle C2 has equation x squared plus y squared minus 20x minus 10y plus 89 equals 0. You have to find the equations of any lines that are normal to both C1 and C2, justifying your answer. So for part C of the question, we've got circle C1, x squared plus y squared equals 16. This would have center at the origin, and it would have a radius of 4. And if we consider the circle C2, we have x squared plus y squared minus 20x minus 10y plus 89 equals 0. So we have x minus 10 squared plus y minus 5 squared minus 100 minus 25 plus 89 equals 0. So x minus 10 squared plus y minus 5 squared equals 36. We would have a center at the point 10, 5. We would have a radius of 6. Now, so we know that all normals to a circle must pass through their centers. So there is only one common normal, the line through both centers. So if I draw a diagram, we've got here both circles, C1 and C2. Let's just label them. Rather, here we've got C1 and here we've got C2. And we've got the normal over here which passes through both centers. And what we need to do is find the equation of this normal. And the way we can do that is to think, well, what we can do is find the gradient of this line, and it passes through the origin. So the gradient that's equal to 5 over 10, which is 1/2. So that's what the gradient is. It passes through the origin, so therefore this line, we can say about it, well, the normal to both C1 and C2 would have equation y equals 1/2 x. So here we will label this y equals x upon 2. For part D of the question, we have to find the equations of all lines that are a tangent to both C1 and C2. You may find the following Pythagorean triple helpful in this part. 7 squared plus 24 squared is 25 squared. Now the way to think about this, we've got both our circles C1 and C2. We've got a centre at 0, 0 and a centre at 10, 5. What we need to do is find out all the equations of the tangents to both curves. Well, if here we've got a radius of 4 and here we've got a radius of 6 and the distance between here and here horizontally is 10, well the 4 plus the 6 is 10. So we have a tangent which is vertical as shown here, and then we've got some tangent here, another tangent here, and another tangent here. And what we need to do in this question is find out the equations of all those tangents. So here you can see all of those tangents where we've got our circles C1 and C2, and we mentioned why here we've got a vertical tangent, and the reason for that was we mentioned if this distance between here and here is 4 and then between here and here we have 6, and the 4 plus the 6 is the 10, and the distance horizontally between this point and this point is 10, which is why we must have a tangent at x equals 4 then. So let's write that down. So what we are saying here is the horizontal distance between both centres is 10, and the sum of the radii is 4 plus 6, which is 10, which means there is a vertical tangent at x equals 4. Now, if we think about what we mentioned in part B, when we had a line which is a tangent to some circle C, we ended up with this result here. And so the tangents we see described by this diagram will satisfy those equations that we found in part B. So using B, the other common tangents y equals mx plus c would satisfy c equals, well, one curve has a centre at the origin, which means that A is 0 and B is 0, and we know that the radius in that situation is 4. So we have C equals 0 minus 0m plus minus 4 times by m squared plus 1 square rooted. So this is for the curve C1, and this is equal to, well, we've got here 10, 5, so A is 10, B is 5, and if we substitute that into here with R equaling 6, we would have 5 minus 10m plus minus 6 times by m squared plus 1 square rooted. So this is for curve C2. So if we simplify this even further, we have c equals plus minus 4 times by m squared plus 1 square rooted equals 5 minus 10m plus minus 6 times m squared plus 1 square rooted. Now here we need to think about how many solutions we'd have, and let's make a quick note on the side in rough. If I have plus minus 4x equals b plus minus 6x, well, let's think about the combinations. If I have plus 4x equals b plus 6x, that means we would have minus 2x equals b. But what happens if I've got minus 4x equaling b plus 6x? Well, taking 6x from both sides, we would have minus 10x equals b. But what happens if I've got 4x equals b minus 6x? Well, in this case, we would have 10x equals b. And what happens if I have minus 4x equaling minus b minus 6x? Well, here you can see that 2x is equal to b. So what we have are multiple solutions. We've got plus minus 2x equals b, and we also have plus minus 10x equals b. And that idea can be used to help simplify all of this. What you can think the b to be is 5 minus 10m, and you can think of the x to be the square root of m squared plus 1. So when we come to simplify all of this equation, what we would have is plus minus 10 times by m squared plus 1 square rooted equals 5 minus 10m, and we also have solutions plus minus 2 times by m squared plus 1 square rooted equals 5 minus 10m. And what we really need to do at this point is solve for m. So let's treat each of these equations separately. So if I call this equation 3, and if I call this equation 4, well, from equation 3, well, we've got plus minus 10 times by m squared plus 1 square rooted equals 5 minus 10m. And if we square both sides, now squaring plus 10 times the square root of m squared plus 1 and squaring minus 10 times by the square root of m squared plus 1, it's going to give us the same result. It's going to give us the result of 100, because plus minus 10 all squared is 100, times by m squared plus 1 square rooted, rather m squared plus 1, and squaring the right hand side, we have 5 minus 10m squared. So we've got 100 m squared plus 100 equals 25 minus 100 m plus 100 m squared. So 100 m equals minus 75, in which case we can conclude m equals minus 3/4. So we've got a solution for m at minus 3/4. And if we deal with what we have from equation 4, so from equation 4, we've got plus minus 2 times by m squared plus 1 square rooted equals 5 minus 10m. Same idea of squaring, we would end up with 4 times by m squared plus 1 equals 5 minus 10m squared. So we have 4m squared plus 4 equals 25 minus 100m plus 100m squared. So we've got 96m squared minus 100m plus 21 equals 0. So 24m minus 7 multiplied by 4m minus 3 equals 0. And from here we can solve for m. We would have m equals, well, we have 3/4 and we also have 7/24. Here are our various gradients of those lines m. And now what we can do is find out what c is, and we can find out what c is using the results here. And I'm going to be using plus minus 4 times square root of m squared plus 1. So we know c is equal to plus minus 4 times by m squared plus 1. And if we use this, when m is equal to, now here we've got m squared and here we've got m equaling 3/4 and minus 3/4. So when m is equal to plus minus 3/4, we would have c equals plus minus 4 times by, now here we would have 3/4 squared plus 1 square rooted. So working this out, we would have c equals plus minus 4 times by, now here we have 9/16 plus 1, which is 25/16. So we've got 25/16 square rooted. So I've got c equals plus minus 4 times by 5/4. So in this case, c is equal to plus minus 5. 4 times by 5/4 is 5. And a similar idea when m is equal to 7/24. c would equal plus minus 4 times by 7/24 squared plus 1 square rooted. So c is equal to plus minus 4 times by, now here we've got 7 squared over 24 squared plus 1 being square rooted. And the way we can simplify this result is to use what we were told in the question. If 7 squared plus 24 squared is 25 squared, that would mean that 25 squared minus 7 squared is 24 squared. And the reason I want to do that is because what I can do now is write the one with a common denominator of 24. So I've got C equals plus minus 4. Now here I have 24 squared plus something over 24 squared. Now 24 squared, evaluating that, that's just 7 squared. So we've got 7 squared, and then 1 I can rewrite as 24 squared over 24 squared, which is 25 squared minus 7 squared. And then all of this will be square rooted. So we've applied this idea that 25 squared minus 7 squared is what 24 squared is. So if we simplify even further, well, what we will end up then in this case is C equals plus minus 4. And here we've got 7 squared plus 25 squared minus 7 squared. So that's the same as 25 squared over 24 squared. Then square rooted. So we've got C equals plus minus 4 times by 25 over 24. So in this case, C is equal to plus minus 25 over 6. Now we've got different values of C. We've got plus minus 5 and we've got plus minus 25 over 6. And if we go back to our diagram, well, here clearly we'd have a negative y-intercept, and here we've got a positive y-intercept. And this line would cross at the same point 5, and this point over here would be minus 25 over 6, and it's got a less steep of a gradient than 3/4. And so what we can conclude from all this then, all of the equations of the tangents, we have x equals 4, we talked about that. We have y equals 3/4 x plus 5. Y equals minus 3/4 x plus 5. And we also have y equals 7 over 24x minus 25 over 6. Here are all the equations of the tangents.